Okay friends, welcome to the 22nd module of AI, and in this particular module we'll be talking about alpha beta cutoffs. Remember what we have done so far. We have looked at game playing algorithms, we have specifically looked at minimax algorithm in our previous module. We have looked at how the algorithm is written, how the calls are made, and the recursive nature of the algorithm, the winding, unwinding phase, and all that we've discussed. And we have also introduced alpha beta cutoffs in the previous module. In this module, we are going to see exactly how alpha and beta cutoffs are applied to different phases of this algorithm and how it can improve the performance of the algorithm. Alpha and beta cutoffs are very simple. As I said, alpha cutoff is applied at minimizing layer, beta cutoff is applied at maximizing layer. What it's going to do is going to eliminate the branch which is never going to be used for decision making. Okay, the decision is already made, and the exploring that additional branch is not going to change the decision. So what's the point in exploring that branch? So those branches are to be eliminated using this method, and we'll soon see that if you do it carefully, it is possible to prune even half the tree. So it's almost a 50% advantage that we get. And what we are going to do here is we are going to talk about alpha and beta cutoffs, and we are also going to have a recursive algorithm like we had in the previous module. We are going to refine that algorithm with the addition of alpha and beta cutoffs. And this is going to be the best if the moves are ordered perfectly. We'll see one example of that as well. Remember, let us recap. Alpha cutoffs are applied at maximizing player. Okay, at minimizing player. But who is doing it? The maximizing player. We do it. Beta cutoffs are applied at maximizing layer, but who applies it? The minimizing player. Now, if we again look at that, you probably will realize that and are applied at alternate plays. Alpha cutoffs are applied here, then the next layer alpha are not applied, beta is applied. Next layer alpha is applied. Interestingly, the alpha cutoffs are applied at the minimizing layer, and we'll see how it is done and why it is so, and the vice versa. So at one layer, we apply one type of cutoff, and the other cutoff is actually decided at that layer, which is applied in the next layer. It's seemingly quite complex, but we'll soon see how we can make it simple. We'll need to in fact, it is basically the same computation. We have some threshold value, and if while we are exploring that node, it goes beyond that threshold value, there's no point in exploring that branch. Now, it's a maximizing threshold or minimizing threshold, depends on the layer. So we have two cases, if you remember, two cases. In one case, we are getting a worst value, so no point in exploring. In the other case, we are getting a better value because it's the opponent's move, and is not going to choose that better value. There is no point exploring it. So both threshold values are basically done. But if you just negate those values, again you can just choose that value and maximize, because minimizing case you just multiply it by -1 and you get the same answer. So point is, basically what we are doing is the same thing. Alpha and beta cutoffs are basically the same thing applied at different layers, and if you negate that thing, alpha and beta is same cutoff. Alpha is basically choosing the lesser value, beta is talking about the higher value, but if you negate that, you are only talking about the maximum. You are not talking about anything else. Now look at the example shown, which is we have already seen in the previous module. This example: A has two children, B and C. B has F and G, while C has H, I and J. Now when we explore F, we get 5. We explore G, we get -3. Because it is the opponent's chance to play, he will choose -3 and not 5. So what is backed up is -3 and not 5. The same case here, when we start exploring C, H gives us 9, so that is good, but then I gives us -9. Now once we get -9, there is no point in exploring further that particular child, because the opponent is going to play, and we know that opponent is going to get -9 or less, because if the third one gets -10, opponent probably will play that, but opponent anyway can always play -9. So it is guaranteed to have -9 or less. So there is no point. I already have -3. So I have that value -3. Anything less than -3, I am not going to play this thing. So this is the highest value threshold that I am guaranteed, -3. If I get more, I will use, otherwise I won't get. Okay, I won't choose that. So I will not choose C. If I guarantee -3 from B, there is no point choosing C. So there is no point exploring any other node after I. So this is alpha cutoff. Now you can see that it is decided at the previous layer. Okay, -3 is decided at layer 2. we are applying at layer 3. Remember, this is something which I have already told you. So deciding something at layer n, applying it at layer n plus 1. The other thing, this is my minimum value, minus 3. If I get more than that, I will accept, otherwise I will not accept. This is minimum value, okay. And it applies at minimizing imply. But who is doing it? We are doing it, okay. It's our choice. So it is applied by maximizing player. Now let us look at the next case. This is beta, okay. Now look at the same thing which we have already seen. There is no difference. And JK applied, you get, because that the third layer is maximizing layer. Out of 5 and 3 we get 5, so that is backed up. Minus 5 and minus 3, that is minus 3, that is backed up, because it's the best thing, okay. Minus 5 and minus 3 is better for us, less dangerous. But then 5 and minus 3 is backed up because it is the opponent who is playing. Similarly, in the case H, you get minus 9. That minus 9 determines, now that is happening at maximizing layer. You can see that for I there is one child with value 5. Now what's the point in playing I? Opponent will not play I, because minus 9 is the minimum value. Opponent will only play if I get a lesser value than that. If opponent is getting a higher value, opponent is not going to play. Now this is, remember, this is the minimum value. Opponent should get a lesser value, will play, otherwise it will not play with higher value. So anything more than minus 9, opponent is not going to play. So even if it is not 5 but minus 5, opponent is not going to play. Once that happens, the rest of the nodes are not important. Remember, who is playing it? The minimizing. I is played by the opponent, the minimizing player. It applies at maximizing ply. So that is what is shown here. And here also, the next slide also talks about one more issue. Though the value is decided at the previous layer, there is a global value which has an effect. In this case, when I am exploring L and M, L will give me 1. Okay, so that is the local beta value. I get 1. If I get less than 1 only, then there is a point in exploring the children of M, otherwise not. But I get 2, so there is no point exploring it. But then there is 2, then it is, yes, 2 it is not, no way. If it is minus 1, there is no point, because eventually we are going to play and we already have guarantee from B that we get 3. So if anything else is guaranteed, less than that is guaranteed by C, we will not play C. So this threshold, though it is 1, which is local, should be applied, will not use 1 but will use 3, which is a value, higher value, which is coming, is a global value. So the best value for us is through B, 3. L is good but not as good as B. So our preference is B, and because of that there is no point exploring. Once we get L as 1, in fact there is no point exploring the other branch of H. That is basically a maximizing alpha cutoff. Actually this is a case of alpha cutoff and not beta cutoff, though but I just wanted to stress on this point, so I have done it. But otherwise this is an example of alpha cutoff. 1 is less than 3 and there is no point, because an opponent can get me that. I don't want to. In fact, our opponent will not play H because I'm guaranteed 1. So there is no point doing it. I'll just choose B. There is one more example shown on the screen, 21.4 figure. Now look at that. I have explored B before the others. Okay, when I explored B before the others, I get 5, 6 and 7. So that's a minimizing ply, so I get minimum 5. What's the beauty? The beauty is that when I explore C, the first child is 2, which is less than 5. What will I do? I won't use that. Why? Because C guarantees me only 2 or less, because the opponent's play. And I've already got 5 from B. So there's no point exploring other children of C. Similarly, when I explore the first child of D, I get 3. Again, this is no good. E is minus 1, it is worse. So there is again no point. And I could easily eliminate others. And I'm not actually eliminating one node, I'm actually eliminating a huge tree. If it is the case that this 5 and 6 are backed up values of 10 plies. What I'm eliminating, J is a 10 ply dip tree, L is a 10 ply dip tree, and so on. So actually the saving is huge in this case. But the point is, I am doing B before others, I get a better value in the beginning, and then which can help me this thing. Okay, if I have started with E, probably I would have explored all the nodes everywhere, because I start with the worst thing and everything else looks better, so I'll explore everything. Okay, so this ordering is actually very, very important in this case. But then how will you get this order right? Remember our discussion about IDA. idea does what? Explores, pass the value back, again explore, pass the value back. What is the point? The point is that once you explore, pass the value back, you know which path is more promising than the other, and you explore them further before others, because once you use idea star with this idea star, remember alpha beta cutoffs are not only applied to minimax but other as well. So when you do that, they become better. Okay, they become better, the first paths become better, we can eliminate more number of branches, so the ordering becomes better. Now we'll look at the formal minimax algorithm. The minimax algorithm again returns the node info object, but then the first three arguments are same as we had in the case of minimax, but then next two are values. One is called current threshold, the other is next threshold. There is no mention of alpha and beta. You will be surprised where they have gone. They have not gone anywhere. What we are doing is, remember what we have done. For one layer, there is a threshold value that we are going to apply. That value is decided in the previous layer. So what is happening is that in a single layer, you decide something which you apply as a threshold in the next layer. And what you decide in the next layer applies to next layer, and so on and so forth. That take turn. Okay. So in case when for example in a maximizing case, alpha is applied while beta is calculated. In minimizing beta is applied while alpha is being calculated, and so on and so forth. So the same thing is happening here, and we are changing current threshold and the next threshold value, and not only that, we are going to exchange it when we are calling. So alpha becomes beta next, and beta becomes alpha in the next one. So that is what we are going to do. We are also going to negate them, and the argument is the same which we had in the previous case. So that is what we are going to do. So current threshold and the next threshold, they change. Current threshold may be alpha right now, next threshold is beta, next case current threshold becomes beta and next threshold become alpha. Okay, so they change their position as well as negate their values. So this is what is the call to this function indicates. The same like the previous case, we invoke function over, and it will have exactly the same code as before. Okay, nothing is different. Node info nf dot path is null, nf dot value is SCF, and return nf, and all that is the same as before. There is no difference. And also the else part, we generate the children using PMG, again the same. Nothing, there is no difference at all. Okay, the second step also remains the same. There are no children, absolutely fine. It's like a leaf node. Treat it like a leaf node. Okay, generate the value of path as well as path is null, and generate the SCF and return it back. And again, why this is null? Because we have reached to a dead end, a draw, or winning or losing by one of the parties. The next thing, the remaining part of the algorithm is different a bit for every child. Otherwise, what we'll have to do is, for every child we'll have to call this algorithm. Remember, that is what we were doing earlier. We are calling the same algorithm and getting the value back and then passing it up. Okay, this is precisely what we are supposed to do. So we are again calling the algorithm, and the algorithm again returns node info object the same way where we have done before. But then there are two important differences. Again, we are adding depth by 1, we are changing the player, but you can see that the position of current and next threshold, positions of them are exchanged and values are negated. Let me repeat why we are doing it. The current threshold becomes, it does not remain threshold next case, it's only setting it. You set threshold in at one layer, you use that at the other. Again, the next layer you set, the next layer you use. For both alpha and beta, it is the case. So when when you're using alpha setting, you're using beta. When you're setting beta, you're using alpha, and so on and so forth. Okay, so that's why we are using this thing and we are exchanging this positions. Okay, the same way the child values, whatever the heuristic value of the child is returned by the algorithm, we are negating it for the same reason we discussed earlier. Now, an important thing, the child SCF value that is returned is more than the next threshold value. Next threshold is being set. So what does this mean? This means that the next threshold is less than the value that we are getting. What does that mean? That this child is more promising than the threshold value itself. Now when this child is more promising, the threshold value will increase. So that's why, and it's kind of getting the better child. So when you get a better child, you improve your best value. That's exactly what is happening. So next threshold becomes child SCF. So that value is improved. And path, obviously, because you get a best node, you get a path to it, like exactly like we've done in the previous case. Okay, we have to also set the threshold for the next level. And please understand, this is a very critical thing that is happening. Let us recap that thing. Suppose if I have explored my B child and I get -3. I've explored this node and I'm getting a better response. Suppose if I from C I get 4, B, C, D. Assume that I have 3 children. A, B, C and D are 3 children. I get 3 from B. From C, if I get 4. So for D, the threshold is not 3 but 4. Why? Because it is better. How it is done? When you get 3, you start that thing as a threshold value. So when you explore C, that next threshold value is 4. So that is hovering on our mind that 3 is maximum, 3 is maximum. But when we get a better value, we get 4. Some child says that I'm capable to produce 4. Okay, B says I'm capable, C says I'm capable to produce 4. Great. What we do is we'll replace 3 by 4 now. That is exactly what's happening, and that's what we mean by setting the threshold value for the next level. Now I'm going to use 4 for the next child and their exploration as my threshold value. I'll not use 3 because I've got a better estimate, a better node, a better child. Okay, that is what is happening here. My child SCF value. Child SCF is current that thing. Okay, the current child's value is better than the threshold value that I have chosen to be best. Now then this is the best. Okay, I am going to use this thing as a threshold. In the next iteration, this thing is going to be used as a threshold, and that's why this part this is very, very important. If current threshold is less than this thing, okay, it's very important again. The current threshold value is less than the child, this thing, the child value. What should I do? Now remember this, we start with alpha, and when we do beta, we negate that. So remember alpha where we have the maximum value. Anything less than that, we'll just skip. So if this value is less, we are going to skip. So the value that we get is, so beta is more, alpha it is less, then we skip. But here we don't need to do it twice because we are negating it. So when that value is true, when we are above threshold, we are below, going above threshold value, there is no point because opponent is not going to let us play that, or neither we are going to play that while it's our move. So in that case, we'll return back, we'll not explore that further. Okay, and remember, eliminating, it is not only eliminating one node, it is eliminating the entire tree. Okay, it is quite possible that I get B and C based on 10 ply deep search, and when I'm exploring D, I can eliminate one child. I'm not only eliminating one child, it's only also a 10 ply deep search tree which is eliminated. So that's something which is really great. At the end, what we do is, once the process gets over, we return the very structure which we returned in the earlier case, same node info structure which we return back. The process is explained in little more depth now. Okay, over function as well as the structure NF has no change from the previous that thing. What we do is we invoke minimax and increase the depth by 1 and change the player and position, okay, or switch the position. Now that switching position is something that we have added. Assign the value returning to child SCF. So the same thing is here, even same thing is there for path. The cutoff is also assigned like we have done in the earlier case. The point is how the first call is made. Remember, the first call is made with the state as a start state. So we say that normally what we do is minimax, current position, 0, current player. This is what we have done. Now we need 2 more values. What is the current threshold and what is the next threshold value? We just say that current threshold is 10, the next threshold is -10. Remember, in our next case, this -10 comes here and 10 goes there. But then they are modified. Why 10 and -10? Because 10 is maximum value that you can get and -10 is the minimum value that you can get. It's very similar to any other function where you calculate minimum and maximum value. When you are calculating maximum value, you start with the minimum value and assign that thing as max. So any other value which is greater than that will be assigned max and so on. So to set the ball rolling, you do that. When you are calculating maximum, you assign a minimum value and then do it. Whenever you want to find out minimum value, you start with the maximum value and so on. So these two values are there for just initialization, okay, with the worst possible value. So any other value which is better than that can take its place. So that is precisely what we are doing. Okay. But then we are also interested in the two additional things which are applied here. So the first call actually includes this too. What about the first call? Well, the first call, we have this current position as the start state and the current player as 0 if we are playing, or current player as 1 if the opponent is playing. So this is how, with that, this module gets over. Let us recap what we have done in this module, what we have looked at in this module. This is an extension to the earlier module where we have looked at the minimax algorithm. We have talked about alpha beta cutoffs to the minimax algorithm. The alpha cutoff is something which is applied at minimizing layer, and the beta cutoff is applied at minimizing layer, maximizing layer. Whenever they are used, they are able to help us remove a branch which is not required for us to explore based on the decision making process. The decision making process already has decided, and now there is no point exploring it further. So it's a good thing that we eliminate that. If we order them properly, we'll be able to eliminate almost half the branch. So that's how we get this thing done. Some of the researchers also worked on this and proved that Nath and others proved that we can get substantial advantage if this ordering is proper. Almost 50% is possible. So that's what they have done, and which we could also see that we have looked at one of the examples in the model where we could seriously see that almost half the nodes are just not explored. Okay, so but that actually depends on the order, and that's where the advantage of IDA star comes into picture. I talked about IDA star. There was a program called Chess 4.5 which used IDA star there instead of the minimax, just for this reason, because IDA star happens to provide alpha beta cutoffs in a far better way than minimax itself. Anyway, but that's it is. But when you apply minimax, instead of 3, we have 4 components of the algorithm. We have 2 more. One is called current threshold value, the other one is the next threshold value. The current threshold value, we are not stating anywhere what is alpha and what is beta. They are continuously changing depending on the situation. Current threshold is alpha and next threshold is beta. The next level current threshold is beta and the next threshold is alpha. So what we do is we just exchange while we call the algorithm. Their positions are exchanged. Not only their positions are exchanged, their values are negated as well, exactly like the previous case, based on the same type of arguments we made in the previous case. With that, we'll conclude this module. Thank you.